Hello and welcome. This is Jerry. I'm going over the Physics 101 final questions from Princeton University. This is part 2, which is one single long question. As I said a second ago, it's a very long question, so I'm just going to get straight to it. So the problem states that we have two identical sleds that start moving at the same time from the same point A. One goes on a bridge with initial speed v0, the other goes down into the ditch with the same initial speed v0 at point A. Assume that v0 is 10 meters per second, the angle of the slope is 45 degrees, and d is 10 meters. So neglect any friction in this problem. It's basically stating that we have a couple of sleds, and one's going from A to B, and the other is going from A to C. So in this problem, we have a few givens. We have the initial speed, we have the angle, and we have the distance. As for equations, we're going to need to use conservation of energy. Remember that conservation of energy simply states that the total energy of an isolated system remains constant. It is said to be conserved over time. So this would be helpful in relation from A to B, as we could utilize the conservation of energy to find certain values that we're looking for, certain variables, such as velocity. So these are the equations we have. We have the kinetic energy is 1/2 mv squared, potential energy mgh, and a couple kinematic equations. You can find them in the formula sheet. The kinetic energy is in the top of the middle column. Potential energy is near the top of the right column, and the two kinematic equations are in the top left and top right column. So for part A, it's asking what is the speed of the second sled at the bottom of the ditch. Now all it's really asking is the speed when it reaches this point. So we have some velocity, and the velocity is equal to what? Now, like I said earlier, we're going to use conservation of energy for problems. So that conservation energy simply states the initial energy is equal to the final energy. It also means that the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. And if we plug in some variables to that, we get mv squared, 1/2 mv squared, v0 squared for the kinetic energy plus mgh is equal to 1/2 mv squared, v being what we're looking for, plus 0, because at the bottom of the hill there is no gravitational energy any longer. So we're just going to isolate v in this case, so we get rid of the m's because you see they're repeated everywhere. We can multiply everything by 2, which will give us mv0 squared plus gh, 2gh, is equal to v squared. Okay, and we can get rid of that squared and just take the square root of this. Now, we're missing what the height is. So we have the distance, 10, but what's the height? One thing to know is that we're given the angle 45 degrees, when we're given it over here. That means it's the same here though, because 45 plus 45 is 90, because we have a right angle over there. And as you know, or as you should know, the total angle of a triangle, I'll just put angle, whatever, is equal to 180. So 45 plus 45, 90. So that's why we have 45 and 45 here. That should be known that when you have the same angle, that means you have the same length of both sides. So this will be equal to 10. If you want to prove that, you can do some trigonometry. What you can do first is find the hypotenuse, and then find the side of h. I'll leave that to you if you'd like to do it, but this is just something that you should know that's equal to 10. So when you plug that value in, you get 17.2 meters per second. And that's the answer to part A. Now part B asks, find the time that the second sled needs to reach the bottom of the ditch. So we have the same process, A to B, but rather than velocity, we want time. So V is equal to V0 plus AT is the equation that we're going to use. Let's isolate T. Let's see. So V minus V0 divided by A is equal to T. But what is A? So the only velocity, well, acceleration that we have is the gravitational acceleration, which goes straight down. This is the acceleration that we care about here. And remember that we have the angle being 45 degrees. So if we do some simple trigonometry, we can see that if we do co in SOHCAHTOA, well, it's ka, not co. Let me fix that up. Ka, which is equivalent to cosine of theta, is equal to adjacent over hypotenuse. Now, if you quickly redraw this to make it look a little easier to conceptualize, okay, this being G, this being A, this being the angle. So the adjacent is going to be A, while the hypotenuse is going to be G. So G cosine of theta is equal to A. So we can plug that in up here, giving us T. Well, I'll just rewrite the equation very quickly. V minus V0 over G cosine of theta is equal to T, which will be equal to 1.04 seconds when you plug everything. And that'll be the answer to part B. Part C asks, is the time that the first sled takes to move from point A to C on the bridge larger, equal, or less than the time the second sled takes to go to the bottom of the ditch? So we just need to find the time of from A to C. With a line right there. So this would be A to C. So the time is equal to what? And for this, we would use one of the equations we had mentioned earlier. X is equal to x0 plus v0t plus 1/2 at squared. I wrote it up top over here. And one thing to know is that we have no acceleration and the initial distance is 0. So we could write it very simply. This is equal to v0t, because this is 0, this is 0. And we're just trying to find t. So x over v0 is equal to t. We know what x is. X is equal to the distance, which is equal to 10 meters. So we have 10 over 10, 1 second. Which means that it is shorter. The time is shorter. There's shorter time from A to C than A to B. Alright, now for part D. Part D is a little more complicated. There's an extra bit of equations that we have to use and some knowledge that you need to be aware of. So the question states, suppose that instead of two sleds, two spherical snowballs of the same mass are released at A with a center of mass speed of v0. What would be the speed of the second ball when it reaches the bottom of the ditch? Assume that the two snowballs roll without slipping. Okay, so one extra thing you need to know is that above, well, beyond simply kinetic energy and potential energy, we also have rotational kinetic energy. That's just an extra little bit that we have to work with, because we're going to work again with conservation of energy for this problem. Now, you can find the equations. First, I write them down quickly. That we have kinetic energy. I'll put kinetic energy of rotational is equal to 1/2 I omega squared, omega being angular velocity, and we have V is equal to R omega. And to make it more useful, you can have omega is equal to V over R. And we have I of this full sphere, I being the inertia of the sphere, 2/5 mr squared. You can see them in here. We have the kinetic energy in the top left column, and we also have the inertia of the full sphere in the middle left column, And in the top middle, we have v equals r times angular velocity. So with this, we do the same thing we did for part A, but we have an additional bit of equation to work with. So the same thing, that the energy is equal to E1, E initial is equal to E final. So E initial is going to be equal to 1/2 times mv0 squared plus mgh, so same, except we also now have the 1/2 inertia times angular velocity squared. Well, for the final, same thing, 1/2 mv squared plus 1/2 I, it should be initial over there, omega squared. Now, let's just make them equal to each other. So 1/2 mv0 squared. Well, actually, just keep them as they are and just, yeah, okay, yeah, I'm just going to go like this. Plus mgh plus, at this point, I'm going to replace it with the proper replacement, where we have the inertia of the full sphere. So I'm just going to put what that's equal to, 2/5 mr squared, and omega squared, and over here, omega squared will be v squared over r squared. So we have v squared, v0 squared in this case, over r squared. And this will be equal to the 1/2 mv squared, plus, basically the same as I just wrote, 2/5 mr squared, v squared over r squared. So the only difference being that we are using the final velocity instead of the initial velocity on the right, just as in part A. Now, you notice that m is everywhere. Just get rid of all the m's. You can also notice that there are squareds that can be cancelled out. So if we rewrite it, we have 1/2 v0 squared plus 1/2 times 2/5. Let's just make that 2/10 immediately, times v0 squared is going to be equal to 1/2 v squared. I'm definitely missing something. Yes, plus mgh, yep, is going to be equal to 1/2 v squared plus 2/10 v squared. Okay, now let's just one little bit more of simplifying. So we have 7/10, 1/2 plus 2/10 is going to be 7/10. v0 squared plus mgh is equal to 7/10 v squared. Now I'm going to divide everything by v squared, by 7/10, which will cancel out the 7/10 here, and this will now be 10/7 times mgh. It's going to be equal to v squared. Just get rid of the squared, take the square root, and that is the end, except this whole time I've had these m's, which are no longer relevant. I canceled it out earlier. So it's just 10/7 times gh. And the result of this, if after plugging everything in, is 15.5 meters per second. Now that's the end of this question. I hope you enjoyed it. I'll be making more videos from this exam and more physics videos in the future. And thank you for visiting.